Okay, here's a full explanation of how to solve distance of closest approach problems. Basically, what closest approach is if you have a nucleus, let's say of the 207 82 lead, right? And then we're trying to fire an alpha particle at it. So we would try firing it directly over here. Basically, what would end up happening is that somewhere around, I don't know, let's say here, the alpha particle would actually start getting repelled and go in this direction. So this radius here from the lead nuclei to the alpha particle is the r, and that is the distance of closest approach over there. So, no. All right. Now, to solve this type of question, we need to first make the realization that the kinetic energy here at the point where it is rebounding, that point there. So if you take the alpha particle like that, that point, this point here, the kinetic energy at that point is equal to the electrical potential energy. So taking those equations now, just do that. So the equations of each are 1/2 mv square, and that's equal to kq1q2 over r. So these are known equations, and we already have the kinetic energy right there. So we can pretty much just ignore this for now. So let's focus on solving this. First thing we want to do is we want to calculate for r, so we will rearrange it for solving for r. In this case, the equation will be uh, r equals kq1 q2 over ek, since we basically already have ek here, right? So then next we will have to input the values for q1 and q2. So q1, let's take this as the charge of the lead. So let's say it's 82, since that's the atomic number here, the number of protons, which is also equal to the charge, into the value of elementary charge, which is 1.6 times 10 power minus 19 coulomb. And let's do the same for Q2, which is an alpha particle. So this is the PB, this is the alpha particle. So Q2 is 2 times 1.6 times 10 power minus 19 coulomb. So putting this into a calculator will yield that will equal to 1.312 times 10 power minus 17 coulomb. And Q2 will equal 3.2 times 10 power minus 19 coulomb. So now we have that. We can multiply it by another constant, which is k. So getting that from the data booklet, the constant k is 8.99 times 10 power 9 newtons per meter square. Newton meter square per coulomb square. So now we have this. Basically, these cancel out, right? So we have the 8.99 times 10 power 9 Newton meter square per coulomb square. That is there. And then we have the 1.312 times 10 power minus 17 coulomb into 3.2 times 10 power minus 19 coulomb. So all of that is over the initial kinetic energy that we were given, which is 5.9 mega electron volt. So converting that to joules, so need to basically take 5.9 times 10 power 6, and then divide it by 6.242 times 10 power 12, which gives us 9.453 times 10 power minus 13 joules. So that is what goes here. So rewriting this equation, that is equal to 9.453 times 10 power minus 13 joule. So this column square over here, since you have C and C here, so these all cancel out. Nope. That cancels, that cancels, that cancels. So now we're left with just these, Newton meter and then joule. So 1 joule is also equal to basically 1 Newton meter. So that's that. So this also cancels here, and then this one cancels the square. So now we're just left with a meter. So cancel, cancel, cancel. So that's just M. We're going to be left with meter at the end. So I'll plug this all into a calculator now. That gives us a final answer of 3.99277 times 10 power minus 14, which is about 4 times 10 power minus 14, which is exactly what the original question was stating. All right.